It's my pleasure to be moderating these gentlemen on a project that started at FiRe a couple of years ago, and it's really beginning to take off, and they're going to tell you all about it, but it's so exciting. I mean, what happens here at FiRe in terms of big thinking, and we're talking here now about basically monitoring the planet, and at least in terms of Earth, it doesn't get much bigger than that. And it's energy systems, it's just how things are working. And it's a very interesting moment to be having this panel as our second gigantic, unprecedented hurricane goes through the southern United States, the second one in just a few weeks, which certainly we're going to hear about. And how do we develop modeling systems? How do we make it? And I hope that we can talk about how we make it accessible too, because these are really complex collections of data, of analysis, and how do we bring it down that people can understand it, especially those that are a little skeptical about what might be happening on a global scale. So how do we make it understand? But I'd like you gentlemen to each take a minute or two and just tell us who you are and a little bit about yourself.
Okay, my name is Lee Hall. I started out as a software developer. I learned to code in the early 70s or mid 70s before there were personal computers in a high school. So I really got advantage of an education system. I grew that into becoming system programming, system architecture, and then enterprise architecture. And then I got to a chance to start developing small businesses and very large companies, which was challenging in different ways of startups. And so now I'm doing a lot of different things, from helping business operations in different businesses to helping people understand how to do integration better.
Brian?
My name is Brian McInerny. I'm the Senior Hydrologist at the National Weather Service Forecast Office in Salt Lake City, Utah, just down the road. And my end of things is I do water supply forecasting. I do post-wildfire debris flow warning. I run the flash flood program, and I'm also the climate change person for the office. And I was here last year. I was asked to be on the panel for Chasing Coral to talk about climate change. And that was my first experience with FiRe, and I was astounded at the amount of science and technology, and the level is so raised at this group. And while I was here, I started noticing they were doing higher level math and statistical analysis on a lot of different subjects. And I wondered, could we apply this to what we're doing in water supply and weather forecasting? And I talked to Mark, and he hooked me up with E2MS, and I've been with them this past year. And it's a very exciting time because we're trying to catch up with a changing climate that's much faster than what you see in the press. We're dealing with this on a daily basis when it comes to winter storms. They're less frequent, they're more intense. Thunderstorms are much more intense. We have flash flooding that is killed 21 people in 2015. One thunderstorm complex killed 21 people in one event, and we're trying to keep up with this. And seeing all this great science and technology really stimulated what I do. I've been doing this for 28 years. So it was really a well-timed event that I was invited last year and that I've been with E2MS.
So Murray?
Good morning. I'm the co-founder and CTO of Aptage, which was a fire starter last year. It's my third fire. And I'm so excited to be a part of this community and the intellectual stimulation and the range of problems I get to work on. I'm a PhD in mathematics from Berkeley. I'm a retired IBM distinguished engineer. Aptage is applying machine learning and applying machine learning to help people become better project managers and managing innovation and bringing risky projects to successful fruition. And that was my passion while I was working at IBM. Since then, I've been I've been not only working on Aptage, but in various jobs as an applied consulting mathematician. And I've been brought into the E2MS to take the vision that these folks have and help them put in place a mathematically sensible approach to dealing with local predictions in the context of the way heat flows and moves and whatever. We'll talk more about that.
Yeah, we'll talk more about that in a second. Ross, at the end there?
Yeah, still here. Hi, everyone. I'm Ross Palomaki. This is my first time at the FiRe conference, but I actually grew up here in Park City, so it's pretty cool to be here in my hometown at such a neat event. I recently completed my master's degree from the Environmental Science Department at the University of Virginia, and my research centered on mountain meteorology specifically. So I had the opportunity there to work with a number of hydrological and meteorological models. And so I joined up with the rest of the E2MS team earlier this spring. And yeah, there I've been just working since the spring.
Great. So it's so fascinating to me, casually outside or here, just to hear the amazing people that are here. I know everybody, that's part of what's so fun about this, when you find out what people are doing. So Lee, you are the project manager for E2MS. And kind of set the table for us here. What happened a couple of years ago at FiRe, for those of us that weren't here, and what exactly is the project?
So E2MS was the 2016 CTO challenge, and you really have to give respect to people that sign up and do this. They're busy right now. They're working, and while you're eating dinner, they'll still be working.
Yeah, just a second. I know a lot of you are involved with this. Could you raise your hands? Yeah, I mean, it's a typical FiRe community project.
And there's people in Europe that didn't make the trip, et cetera.
Yeah.
So one of the key words here is monitoring. So what we're trying to do is improve the level of monitoring we're doing to not only understand the energy flows that we sort of understand today to predict the systems or understand the systems that make up the Earth, but to understand the interactions between them. That's really an important element. So some of the energy flows may be brute force, but there may be, as we've probably experienced personally, right, there's subtle things of energy that actually enable those brute force elements of energy. So the objective is to be able to show these interactions, not only for the purpose of commercial value, but also to help communicate it to communities, to governments, policymakers in a way that's visual and understanding. So, we see the work that SKI is doing. How can we communicate the types of things that they're doing around our Earth systems to really improve our understanding, not only to the scientific community, but to society and governments, et cetera.
So it's a community really right now, a sort of loose community.
It is a loose community.
Ever going to be a company or a attempt to create?
So part of what we're going to tell you today is about a proof of concept that really these gentlemen are driving.
Okay.
And that's going to decide where we go next. Is this feasible? Well, they're going to tell you it's feasible. Now we got to prove it, right? And when we get there, we're going to be able to demonstrate this to different organizations and decide where we go.
I just want the app when you develop it. I want to really access that.
Well, we're going to try and put it on gigantic screens.
Yeah,
so
right. Well,
really,
that's even
really
better.
get the visual effect.
Yeah, because this is big. Right. Anyway, so Brian, tell us a little bit about how this is being actually done.
So when I was sitting in the audience listening to the different topics, I thought, can we do better with the National Weather Service forecast when the Colorado Basin River Forecast Center, how we do water supply forecasting. We've been doing this, long time. And the models that we use and the equations that we use were developed in the early 70s, roughly 45 years ago. And we tweak these consistently. We try and improve these models, but they're limited because they're hydrologic models. And these equations, like I said, 45 years ago. So while I listened to the different groups talk about it and the different levels of math, I thought there's a different way we can do this. And we need a proof of concept because it might be a good idea, but we need some way to illustrate the beauty of this. And so what I thought is we could use this for water supply forecasting. And just to give you an example of where this is. And I did this kind of on the back of a napkin just recently. So when you think of Utah, it's actually quite cheap water here compared to Western US. It's $273 for an acre foot. And how we measure water volume is an acre, think of an acre field filled up about a foot deep. That's the volume of water. And we measure it from April 1st through the end of July. And what that volume is what the water districts charge for and what we forecast for. So for this specific headwater point I chose, has 118,000 acre feet that runs during the springtime. And it's roughly at $273. It's $32 million of water that moves past this. And the water districts come to us all the time and say, can you give us a better forecast? Can you do better? And if you were to do no science at all on this point, and just say, this year, on January 1st, we're going to go with average, your error is 33%. 1/3 of the water is unaccounted for. And so then you bring us into the equation and we add value to this. We bring the error down to 25%. And that's roughly $8 million improvement, but it's 29,000 acre feet that you still can't figure out if you're going to have it this year or not. And then I thought, what if we just have a moderate goal? What if we just try and improve this forecast by 5%? And what you find is the error goes down to 24,000 acre feet, and that's mean absolute error. And it's an improvement of $1.6 million over the current forecast for this one small point. And that's $1.6 million that the water districts can then manage. They have this commodity that they can figure out what to do with. And then I thought, well, this is just one point. You really don't want to do it one point. How many points are in the Colorado River Basin that are headwater areas? And there are 223 of these points. And at $1.6 million improvement, that's $359 million in water that they can manage in a better way. And then I thought, what if we just take this to the West Coast, to the Pacific Northwest? That's $1 billion in water. And that's at the low Utah prices. It's probably about 10 to 15% higher depending what the water rates are there. So the value that we're giving them, we're saying in the Colorado Basin, $359 million of water that you can now manage much better with just a 5% increase in the forecast skill. And when I was here last time, I talked to the assistant general manager of one of the larger water districts here in Utah. And we're just like this. We're on a panel, we're on a break, and I just said, would you pay more for an improved forecast? And the guy didn't blink an eye. He just said, absolutely. We would do it right now. It is so critical in a time with a changing climate, with a warming climate. The Colorado Basin is getting drier. Storms are less frequent, but they're more intense. And you get these events like 2017 that had incredibly dry for 5 years, and in 2 months' time, they went from drought to flood control. If we can improve on this, that would help us out a great deal.
Is anybody actually, I mean, this is just a pilot project, a kind of, as you said, back of the napkin.
Yeah.
What would it take to get that out? It sounds complicated to get it out, even to the Colorado River Basin, the 223.
I think once we get the proof of concept and we can show that we backdate our analysis and see how we did, then we can go forward with that point.
Yeah, fascinating. So Ross is going to give us a little bit of the meteorologist point of view, and we were just talking for a second back behind the curtain about obviously this moment we're in right now with hurricanes, and we were just hearing from Brian about weather change locally everywhere, and maybe you can help us understand how what you do and what you think about is fitting into this idea of better monitoring the Earth.
Yeah. So as Brian mentioned, the current pattern of precipitation and storm events and everything, it's getting more severe. It's getting a little bit more unpredictable. And so what I like about this project and the way that kind of our models are being structured is here in Utah, and actually throughout the Intermountain West, we have a really dense network of observations. So that could be from weather balloons that are launched or surface weather stations that are constantly collecting data. And in some areas, including the watershed where we're looking at for this project, they're actually deployed in a denser network than like a continental U.S. model would actually pick up. So if you have, you might have a resolution on these larger models that are 10 or 20 kilometers for one grid cell, but we have maybe 3 or 4 different stations within that same grid cell. So we're able to really use the very local conditions and get a better understanding of what the variability is over a short distance and how that might affect the forecast of this water. The other thing that I really like about how everything is structured in this model that Murray will talk about later is if it's very easy to move to a different region when we get there. So here in Utah, we're concerned mostly about the just the local weather, winds, things like that. But if we want to move up to Seattle, for instance, then all of a sudden we're closer to the coast. Maybe the sea surface temperature is playing a much larger factor. But the model is flexible enough that we can bring in these new data sources that are more or less important for where we're moving regionally.
Can you keep up with the pace of change right now? I mean, you're even describing, Michael, happening right now, that normally this wind shear, I guess you can correct me if I'm wrong here, but comes down to slow them down a bit so they're not as powerful when they hit land. But it sounds like that didn't happen, I mean, which was unusual. I mean, are you able to keep up with what's happening with climate change?
I mean, so that's not my exact area of expertise, but it seems like the people at the Hurricane Forecast Center, they're having a similarly tough time. They do the best they can with the models that they're working with, but conditions are changing so quickly, and I think that's part of what caught everybody off guard with this current storm. So.
Yeah. So Murray, you're our mathematician that's going to make sense of all this and explain it to us, right?
That's the hope.
Yeah.
It turns out maybe it'll even true. So there are some insights here that I was able to. What I do is I tend to look at what has been done in adjoining fields and bring that to this field. So I get to sort of take an overview. The insight here is that the big hydrological models work at a global scale. Energy flow works at all ranges of scale. So there's local the manifestations of energy flow are snow cap and precipitation and weather moisture, ground moisture, and whatever. And the big models don't take into account, as Ross said, all that data that we have. So what we're going to do different is take much more advantage of the local data. And there's actually a lot of hidden effects in that data. But what's really cool about modern machine learning is that you, without even knowing what those effects are, you can learn what the impact of those effects are. There's a lot of magic in neural nets and whatever. And so the key thought here is, rather than try to keep tweaking the big hydrological models, let's learn as much as we can about the local data, from the local data, okay? And local data, a simple example is if there's a lot of snow upstream, probably there's going to be a lot of water downstream. However, the actual lag times and whatever, we don't know those, but we can learn them. And so we're going to, and we can apply the same kind. So what's cool about this is that it involves technology which is current but sort of well understood at this point. There's really strong techniques to do this kind of learning. What kind of learning and whatever, we're doing some experiments, but we have some good ideas, and that'll become something we do. And then, as Ross points out really nicely, is once we get that whole framework put together, we can do what I would like to call as mass localization. We can find out the next model that works for the next situation, and we're going to take advantage of some of Judea Pearl's causality models. And so it really is sort of the current mathematical approach, applied math, to this very local problem. Yeah. And we're highly confident this is going to work. Why wouldn't it?
Sounds pretty, and
yeah.
Like a lot of these panels, we've now come to the moment where we would like you all to participate. So if you want to ask a question, don't be shy. But I did want to ask you all, well, it's interesting. This reminds me, I'm in biology, and it actually reminds me of what's happening in some ways with the human body and other organisms right now.
Absolutely.
Yeah, our ability to collect the data has grown exponentially, and our ability to understand it, we're grappling with that question too, and a lot of it is very focused and localized. But how long does it take, and how do you build out the big model where you can take these localized examples?
I got a great answer.
Yeah.
It depends.
That's not a great answer, Murray. It's an honest one.
It's tried and true, right?
Yeah.
I'm actually working in a couple other biotech kind of situations, by the way.
Yeah.
And the techniques we're using here are similar but not identical to the kind of techniques we're using there.
Yeah.
But it is all in the same constellation. There's an awful lot of information to be gleaned from these highly complex interactive systems. If you try to model them in the classical way that like the hydrological model is, build the set of equations, you'll die. That's not going to work,
Yeah.
right?
So a good example of that is the snow that we see out in the mountains right now. In roughly 2035 to 2065, areas that are 100% snow covered in the Wasatch Mountains, these are the mountains we're in right now, are going to be covered in 50% or less. And then by 2070 and 2080, that snowpack is only going to be at the highest peaks, and we're going to have a rain-driven hydrology. We're not equipped right now to do water supply forecasting if our water comes in the form of intense thunderstorms during the winter season, and then it's followed by long periods of high pressure. We're not cut out for that, but we're a big agency, and it takes us a long time to kind of evolve. And that's why when you think of the system right now is evolving so fast, we need something now that's a different approach.
Yeah. Yeah, and these, like biology, these are natural systems, and they are constantly changing, and we're changing them.
Right.
Yeah.
Let's move over here to a question.
Yeah, I'm going to apologize for asking for just a little recap of some things that were said earlier in the conversation. So the first is, what's the major benefit that you see arising from much more accurate water supply forecasts? And then what needs to happen in order to produce those forecasts, if you don't mind?
So the biggest benefit is the water supply, the water districts. They have a commodity that every year, a quarter of that commodity, they don't know if it's going to be there. They don't know if it's going to be way more than they need. And so if we could say, this is what you're going to get with a degree of certainty, then they can manage that water. They can charge different for it. They can move it from high reservoirs down to low reservoirs. They have a better idea of how to do that. And frequently they're frustrated because they don't know. So they wait, try and take the most conservative approach. And in 2017, we went from drought, 2 months' time where we had 300% precipitation. They could not dump water fast enough, and people died downstream because the flows were so high. And they said if we had a better forecast, we could manage this better. And the other part of your question was, let's just see if we can improve this by 5%. If we can do that, then that was that financial analysis that I saw. That's incentive for them to embrace this better forecast.
Great, thank you.
That's fascinating.
I guess based on that, I guess we're hearkening from Deer Park, the mountain biking capital of Utah in future years.
Right. Right. Come mountain bike, Deer Valley.
Yeah, I love mountain
So
biking.
in the land of good intentions, some of you who know me may not be surprised by this question, but I'd love to hear the specific goals and timeline of implementation, because the challenge of good intentions is just that, that it's the try and not do. So what are the steps, measurable steps, that you anticipate achieving in the next year, for example, where we can come back and say mission accomplished for the year's objectives?
So Ty, how timely of a question.
Yeah.
So we're going to be having a meeting later today with a brand new resource that's come forward here at FiRe and set those timelines and then work directly with Mark.
Yeah.
And we feel, I got to say, I was just blown away by the person that stepped forward yesterday. I'm not going to make an announcement because we didn't make that agreement yet, but we were struggling when we got here, and we've got a pathway out. So hopefully next year you will see results.
And if I may add, 5% is a very modest goal. I think we're going to do better. but 5% is enough to to actually have an impact.
And so I guess I want to say, we talk about this from a financial perspective.
Yeah.
But think about water is life, right?
Yes.
And we want to make sure we use it better. It's not, we got to think about that so we can be a viable entity. But really, we want to make a difference as well. And this is a key place where not only we have the skill, but, this is going to be a challenge in the next few decades.
It's hard to monetize lives saved.
Yeah. Yeah.
So, but all those benefits are also involved with this. But it's interesting because there's an economic case to be made and that's enough to make this go forward.
Yep.
And it has all these other benefits.
It's not going to be without challenges, that's for sure.
That's right.
Do you guys have any idea of the cost of it to set against that savings? I mean, to get this spread out. I mean, I'm
Yes, we
still
do.
trying to figure out what kind of organization you create.
Yes, we do.
Okay.
This is
a
what
man
it's
who
like
has
to
short
work
answers.
with Murray on a regular basis. You get answers like this frequently.
So
we do, but it's not now.
Murray, you reminded me of those interviews I do where you get yes and no and you're out of questions and you still got 45 minutes left.
Yeah, well, I hoped I didn't do that. But in this case, the answer is yes, we do. It's a real answer. But
Okay.
we don't want to go through that now.
I mean, there must be a good ratio or you wouldn't be up here on the stage.
Absolutely.
Yeah.
One thing to consider is when I ask my coworkers and the managers in the Weather Service, what's the cost of a good water supply forecast? Nobody can give you an answer. They can always come back and say, what's the value of water? But when you say, what's the value of a good water supply forecast? All of my colleagues were like, we really don't know. We do this because we're the Weather Service and we do a service to our community of the U.S. and we do a good job. But you can't really put a number on that. Maybe it's a good project for a master's thesis, but
Well, there's got to be a literal cost, but you may not even know at this point.
Right.
Anyway, we have another question out here.
One of the things I've been thinking about is a 5% improvement in accuracy in a system that's predictable is one thing, but we've been talking about what kills people being when the system does something unpredictable, right, when there's a chaotic event. And if you're looking at a 5% change in that predictable amount of rain, that's great, but really it's the unexpected enormous flood that really doesn't matter whether that's 5% bigger or smaller, it matters whether you can predict that.
right.
So what's the distinction between that improved accuracy you're talking about in a steady state versus really understanding the chaos?
Let's use Oroville Reservoir as an example, and we're short on time here, but if they had a better
That's a good
forecast early on, they could have dumped a sizable amount of water. This is out of California that runs into Sacramento. They could have dumped a sizable amount of water, so when that deluge did come in, they didn't have to dump it to the point where they were losing the spillway and to tens of millions of dollars in damage. They knew they were losing it, but they had no alternative. They were out of options. What if we could give them a forecast that would improve on that so they could dump water earlier?
Is that possible?
Well, no, but let me.
That seems different to what I'm asking,
Yeah,
which is,
let me-
yeah, great, but we don't want to know whether that flood was 5% bigger. We want to understand how to not be surprised about the flood at all.
That's exactly it. And so this back of the envelope calculation is useful, but I think your point is really well taken, which is what we really want to do is predict local events with more accuracy.
And unfortunately, we're out of time. That was really fascinating,
Good
you
point.
guys. And
Thank you.
Thank you.
Thank you.